Welcome to this presentation on the independent sample t-test. This is Dr. Amanda Rockinson-Zapke, and in this tutorial we're going to talk about the independent samples t-test. We're going to define it, we're going to talk about when to use it, we're going to talk about the logic behind it, we're also going to talk about the statistics behind it, and then talk a little bit about how to report an APA results section as well as set up a file in SPSS. So let's get started. The independent samples t-test, also sometimes referred to as simply a t-test or a t-test for independent means, is an extremely common hypothesis test in social science research. It's often used in group comparison studies when a researcher desires to compare the mean scores of two different groups. This is often an experimental and a control group, but not always, and we'll get into that later. Because the experimental and control groups are independent, that is, they contain separate individuals who receive separate treatment conditions, the scores of the individuals in the two groups have nothing to do with each other. It follows then that the mean scores for these two groups are independent from each other. And that's why we call this an independent samples t-test. For the independent samples t-test, the researcher needs to have two types of variables. First, he or she needs to have one categorical independent variable with two levels or two groups. Second, the researcher needs one dependent variable that's a continuous variable. And remember, in an independent samples t-test, different from that of like a one samples t-test, the population mean and standard deviation are not known. Before we discuss the independent samples t-test further, it's really important that you have a clear understanding of variables. So let's take a moment and review the definition for the independent and dependent variable. Remember, the independent variable is the treatment or the intervention variable. It's usually that which the researcher manipulates or measures, whereas the dependent variable is the response variable. It's often said that the dependent variable depends upon the independent variable. It's the observed aspect of the behavior of an organism that has been stimulated. Let's take a moment and review variables in the context of an actual scenario. In social science research, a researcher may want to know how two groups differ from one another. Let's say it's a he. He can study two groups after the fact, or he can decide to conduct an experiment by dividing a group of participants into separate groups. In this case, we're going to talk about two groups. He treats them each differently, and then he measures the groups on a specified variable after the treatment to see if there is a difference between the groups. In other words, the researcher divides the participants into groups based on the independent or grouping variable. An example of this may be the type of course that students are enrolled in, or the type of course that he wants to assign the students to. All students enrolled in an online course could be one level or one group, while all the students enrolled in a residential course could be another level or another group. So here we see the independent variable, that's which is manipulated or that which was previously manipulated, its type of course. It would have two levels or two groupings, and just as an FYI, levels is just another word that we often use for grouping or groups in research. So the independent variable is the type of course. It has two levels, both residential and online. Then we have the outcome variable, or the variable that the researcher hopes the independent variable will affect. It's called the dependent variable or the test variable. Let's say here that the researcher is looking to see if the outcome will be different depending on which group, those who take online courses versus those who take them in residence. Another way of saying this is that the outcome variable or score is dependent on the level of the independent variable. So now that we have a good understanding of independent and dependent variables, let's go back to talking about independent sample t-tests. Thus far, we've defined an independent samples t-test. We've also talked about what's needed for an independent samples t-test. Now let's take a look at an example of when a researcher may use this type of t-test. Consider a study in which an educational researcher decides to conduct a causal comparative study to examine if the type of course or the medium in which students take a statistics course influences their learning. Here we see that the medium is either online or residential, so there's two different groups, and the dependent variable is learning, let's say operationally defined as course points ranging from 0 to 1,000. More precisely, there's the independent variable, and that again is type of course. And there are two groups. The experimental group consists of graduate students who participate in a new online statistics course, and the control group consists of graduate students who participate in a residential statistics course. Let's say it's a well-designed research study, and so both groups cover the same exact material and they're very similar in demographics. At this point, the researcher would ask the question, is there a statistically significant difference in students' course points in their statistics course based on the type of course they take, residential or online? And the null hypothesis simply states almost the exact same thing. There's no statistically significant difference in students' course points in a statistics course based on the type of course they take. Here we see, because the educational researcher is comparing two groups on one dependent variable, and let's say that he or she has no information about the effect of the type of course medium on the general population, because after all, this is a new course and thus can't run a one sample t-test. The correct hypothesis testing procedure in this case would be a t-test for independent means. Now let's take a look at one other example. We just looked at an example in which the researcher conducted a causal comparative study. That is, he or she looked at something after the fact. The students had enrolled in the courses, and oftentimes a t-test is appropriate for a causal comparative study. It can also be appropriate for use in an experimental study. Consider a study in which an educational researcher decides to conduct an experimental study by applying media richness theory to his online class. Now, to give us a little basis here, media richness theory is based on the assumption that the use of rich media as compared to lean media results in more effective communication. Theorists really argue that the communication medium, or the more rich that a communication medium is, the more ambiguity and uncertainty is reduced. Considering media richness theory criteria, let's say in an online environment, it would go something like this. Using a video conferencing system for communication in which you'd meet online using video is more media rich than, let's say, asynchronous communication such as discussion board. Thus, if we apply this theory, it would imply that video conferencing, when compared to discussion boards, may result in more effective communication when discussing complex ambiguous learning topics and assignments. Thus, video conferencing may be better for learning complex material than discussion board. So let's say that the researcher wants to test this. The researcher decides to randomly assign graduate students taking a statistics course to one of two groups, the experimental or the control group. Here, the experimental group, we're going to say, consists of graduate students who participate in the online statistics course using the video conferencing medium, whereas the control group consists of graduate students who participate in the online statistics course and use a discussion forum. Again here, because it's a well-designed research study, both groups cover the same material, have the same assignments, and have similar demographics. And because the students are randomly assigned according to Campbell and Stanley in 1963, we can assume that they are equivalent. So therefore, no pretest is needed, and so we don't have to add a covariate into our analysis. And we'll get into that in another tutorial when we talk about an ANCOVA. Here, the research question that the researcher proposes is this: is there a statistically significant difference in graduate students' course points based on the type of communication medium they use in their online statistics course? The null hypothesis simply states that there is no statistically significant difference in graduate students' course points based on the type of communication medium used to communicate in their online course. Again, here we see, because the educational researcher is comparing two groups, the group that's using discussion board versus the group that's using video conferencing, and comparing the difference between those groups on one dependent variable, the correct procedure here again is the t-test for independent means. So the null hypothesis that's being tested in an independent samples t-test simply states that there will be no difference between the experimental population's mean and the control group population's mean, or that the difference between the means will be equal to 0. In our example, again, there will be no statistically significant difference in graduate students' course points based on the type of communication medium they use to communicate in their online courses. Now, let's take a look at the alternative hypothesis. Alternatively, the research or alternative hypothesis will state that the means are different or that they're not equal to 0, and the difference between the means is large enough to be significant. Stated in words, the alternative or research hypothesis for our example that we've been discussing is this: there is a statistically significant difference in graduate students' course points based on the type of communication medium they use to communicate in their online courses. Now let's take a moment to summarize what we just talked about. An independent samples t-test is appropriate when comparing two groups on one dependent variable. That is, there's one independent variable with two groups and one dependent variable. Let's take a look at this diagram. Two groups of the independent variable are formed either on pre-existing conditions or through random assignment. In our first example that we looked at, the researcher examined the difference between two groups based on pre-existing conditions, whether or not the students enrolled in an online course or a residential course. In the second example, the researcher randomly assigned the students to either a video conferencing online course or to a discussion board online course. Let's talk about the experiment for a moment. So the researcher randomly assigned the students to either a treatment or a control group. Then each group was treated by the researcher. Either they received the treatment or they didn't receive the treatment, or they received different levels of treatment. Again, going back to our example, one group got video conferencing and one group got used discussion board. After the two groups are treated, both are measured on a specified outcome. Again, in our example, we used course points. At this point then, the t-test for independent means could be conducted to compare the mean scores of both the treatment and the control group to determine if there is a statistically significant difference, or if a statistically significant difference exists between course points. Now that we understand when an independent samples t-test is used, let's look at the logic behind the analysis. Because the t-test for independent means looks at two completely independent groups, like an experimental and control group, it's necessary to treat each group as coming from completely independent sample populations. To better understand this, let's take a look at the diagram here. This is a diagram often seen in statistics books. Let's start with the top row. On the top row, you see the two separate independent population distributions, one representing the population from which the treatment group is selected, and one representing the population from which the control group is selected. Then, in the middle row, we see that each of these populations has its own distribution of the means. Up to this point, the distributions are completely independent of one another, and you can see that in these two rows. Now we're really going to get to the core of the independent samples t-test. So let's move to the third row. The point of any study with an experimental and control group is to compare the two groups to each other on the dependent variable to determine if they're statistically significantly different. So what should our comparison distribution be? Because we're looking at a difference between means, we have to use a third distribution called the distribution of differences between the means for our comparison. And this is pictured in the third row. This distribution represents all possible differences between the mean of the treatment group and the mean of the control group if the researcher were to conduct a study numerous times. Let me say that again. This distribution represents all the possible differences between the mean of the treatment group and the mean of the control group if the researcher were to conduct the study numerous times. This is found by calculating the actual difference between the means of the two groups of the study, as we see here, the samples represented at the bottom of the diagram, and comparing this difference to our distribution of differences between the means. So this is the logic behind the analysis. So, following this logic, the null hypothesis for the independent samples t-test states, as we've previously said, that there's no difference between the means of the two groups. The null hypothesis first assumes that the two independent populations are equal, or that the differences between them is zero. Next, it states that the means of the two distributions of the sample mean are equal, or the differences between them are also 0. So, when we construct the distribution of differences between the means, the mean of that distribution will be 0. If there is no hypothetical difference between the two populations, then the difference between the means will average out to be 0. Now that we've looked at the basic concepts behind an independent samples t-test and what it does, the logic behind it, let's look at a data set that we could analyze using this type of t-test. Our example earlier mentioned a study designed to examine the effects of an online communication medium aimed at improving learning. Remember, the researcher randomly assigned the participants to either the treatment group that participated in video conferencing or the control group that participated in the discussion board. And at the end of the course, the researcher gathered the course points for both groups. Here you can see what the data looks like after the researcher collected the scores of 10 participants from each group. Remember that these scores are from 20 different individuals altogether, and that the scores of the treatment group are independent of the scores of the control group. And as you can see, we can compute the mean score for each group, and then we can find out the crucial difference between the means. See it here, it's 18.9. By the way, this is all the information that you will need to run the independent samples t-test in SPSS. However, in order for you to really understand how the test works and what these values represent, so that you can properly analyze and interpret SPSS, we need to take the SPSS output. We need to take a look at actually conducting the analysis. So that's what we're going to take a look at next. Here you see the formula to calculate the t-score. You find this value by subtracting the mean of one group from the mean of the other group, and then dividing by the standard deviation of the distribution of differences between the means, which we'll look at in a moment. In our study of learning differences based on communication mediums used in the online class, we would find the S difference for the sample, then compute the t-score by calculating the mean of the treatment minus the mean of the control divided by the S difference. There are, however, a few steps we need to take to get to this point, so let's walk through this analysis step by step. Here you see the notations that we will be using as we talk about the different formulas for calculating the independent samples t-test. I do want to make a quick notation here. The capital N refers to the sample population for the entire study, whereas the lowercase n's usually refer to the treatment and control group, or the different groups within the study. However, sometimes you'll see formulas, and you may even see some in these slides, where capital N is used in both cases. So I just want to make you aware of that as we continue. The first step in conducting an independent samples t-test is to estimate the population variance. You must do this for each of the two groups, so you'll actually have two variances. The degrees of freedom in this formula is the number of participants in the particular group minus 1. For example, in the data we just looked at a few slides back, this would be 10 minus 1, which equals 9 for each of the groups. And then to find the estimated population standard deviation, you simply take the square root of the variance for each of the populations. Here you will see a list of items that need to be reported in an APA results section for an independent samples t-test. So the descriptive statistics, the mean and the standard deviation, the number of the sample population, the number of each group, the degrees of freedom, the t-value, the significance level, and the effect and power. Next, find the pooled estimate of the population variance. This brings us to an important assumption of the t-test analysis, that the two distributions have the same variance. Using this assumption, we find we can use the estimated variance of our two samples from step 1 to compute an overall variance based on both samples. In the formula here, S squared pooled represents the pooled estimate of the population variance. df1 is the degrees of freedom from the first sample, such as the treatment group, and S squared 1 is the variance for the sample that we estimated in step 1. And the DF total is the total degrees of freedom across both groups. This is found by adding the degrees of freedom from both samples together, or both groups together. In the last part of the formula, we see the same thing repeated for the second sample or second group, for example, the control group, and then we add these values together. Now, as we talk about step 3, I want you to think back or recall the diagram of distributions from a few slides earlier. This third step here involves that second row. We have to find the variance of the two distributions of the mean. We do this for each group separately. To find the variance of the distribution of means for group 1, for example, the treatment group, we divide the pooled estimate found in step 2 by the number of participants for that particular group. Even though here it's denoted by capital N1, probably more appropriately it should be lowercase n1. Then you repeat these steps for the second group. For example, the control group. Only divide the number of participants in that particular group. Here you'll notice that if the number of participants in each group is the same, the two variances computed will actually be equal. Now we are ready to find the main value that we will use to compute our t-statistic. Step 4 involves finding the variance and the standard deviation of the comparison distribution, the distribution of differences between the means. This is the distribution on row 3 of the diagram that we looked at earlier. The variance of the distribution of differences between means is called the S-squared difference, and it is found by simply adding the variances from step 3 together. Once we've calculated this value, we can take the square root to find the standard deviation of the distribution of differences between the means, called S-difference. This last value is the one that we will use to compute in our t-score. It's used in the formula that we looked at earlier and that we'll look at again in step 6. Next, it's time to find the critical or cutoff t-value using the t-table. For an independent samples t-test, the degrees of freedom that you should look up on the table is the total degrees of freedom, and this is found by adding the degrees of freedom from both of your groups, df1 plus df2. So going back to our example, remember that df1 was 9, 10 minus 1. If we go back to our example, we had 10 in our control group. That's 10 minus 1, so 9 plus 9 equals 18. That would be an example of how to find the degrees of freedom here, or the total degrees of freedom here. Remember, when you are using the table, to identify whether or not your test is a one-tailed test or a two-tailed test. And if you need a refresher on this, you can go back and listen to this tutorial on hypothesis testing and when you use a one-tailed or two-tailed test. You also need to be prepared to identify your probability or alpha level that you'll be using. And again, for the most part in social science research, this is a 0.05. Now it's time to calculate the t-score, also sometimes referred to as the t-value or the t-statistic. This should look familiar, we've already looked at it, but let's go ahead and review it. You will find this value by subtracting the mean of one group from the mean of the other group, and then dividing it by the standard deviation of the distribution of differences between the means, which remember we found in step 4. In our study of the learning differences based on communication mediums used in the online class, remember, we would find the S difference for the sample, then compute the t-score by calculating the mean of the treatment group minus the mean of the control group divided by the S difference. Now we've come to the point that we can make a decision about the null hypothesis now that we have the critical t-value and we've computed a t-value for our study. Really, the question we want to ask here is the t-value small or large relative to the expected distribution value of t? Let's talk a little bit about this. In fact, we're going to talk about it a little bit over the next few slides. When the null hypothesis is true or it's supported, most values of t should be near 0. We define the value of t that's far away from 0 by looking at the critical values of t, usually values that correspond to the bottom 2.5% or the top 2.5% 2.5% of the area in a distribution, or the most extreme 5%. When the t-value is far away from 0, its corresponding alpha will likely be small, and therefore the t-value will be significant. Let's talk about this a little bit further. So here, if the null hypothesis is supported, or we fail to reject the null hypothesis in a study, what we can expect is that the means of the two samples or two groups should be close together. That is, the mean difference should be near to 0, and the value of the t-ratio should be small or close to 0. On the other hand, if the null hypothesis is not supported or it's rejected, the mean difference between the two groups should be large, and the value of the t-ratio should be far from 0. Now here it's important to note that the value of t can be either positive or negative, depending on which group means happens to be larger. However, the t-ratio, whether it's positive or negative, will be large if we fail to if we reject the null hypothesis, or the null hypothesis is not supported. So let's say that we calculated a t-value for our example, and we looked up the critical t-value, and our critical t-value was 1.96. We would know that if the t-value that we calculated for our experiment was less than negative 1.96 or more than 1.96, that we would reject the null hypothesis. That is, we would say that there was a statistically significant difference between our two groups. However, if the t-value that we calculated was between these two numbers, then we would say that we'd failed to reject the null hypothesis, and there was not a statistically significant difference between the means of the two groups. So to this point, we've really talked about the t-value and calculating if there's a statistically significant difference. But after we determine that there is a statistically significant difference, or a statistically significant difference exists, really a researcher wants to compute the effect size to determine the practical significance of the result. Remember, an effect size is a unit-free or standard index of strength association between two variables. And here what we're going to look at is Cohen's d, and Cohen's d tells us how far apart the sample means were in the number of standard deviations. So let me just give you a quick example of this. A practical significance versus statistical significance. Let's say that in our two groups, remember our online video group versus our online discussion board group, let's say that the course points on our video group was 990, their mean was 990, whereas the discussion board group, their mean was 980. And even though there was a statistically significant difference, what we know by just looking at the scores is that they aren't very far apart, and therefore maybe practically the intervention didn't make a bunch of difference. However, if we looked at this same example and our video group had a mean course points of 990, and our discussion board had a mean score of, let's say, 900, there's a 90 points difference, so our practical significance is larger. So how do we calculate the effect size? We can estimate the effect size of our study after the study is completed by using figures from our results. We really do this by using the formula here. It's the estimated effect size, or Cohen's d. It equals the actual mean of group 1, the treatment group, minus the actual mean of group 2, the control group, and it's divided by the pooled estimate of the population standard deviation. If you remember back to the different calculations we did, this can be found in step 2 of our analysis. We divide by the S pooled because it's our best estimate of the overall population standard deviation, or sigma. Then, once we've calculated Cohen's d here, and you can also use eta squared, but for the purpose here we're using Cohen's d. Once you've calculated this value, you can use Cohen's standards or conventions to decide whether or not the effect size was small, medium, or large. So for going back to the example I gave earlier, if, let's say, the the groups differed by 90 points, we might find that the effect size is large, for example, at a 0.8. Now, the effect size is calculated after the t-value is calculated, or is often calculated after you have the results. However, there are some things that we need to consider examining prior to calculating the t-value, and that is we need to do assumption testing. Remember, parametric analyses require that assumptions be met in order to ensure their robustness. For an independent samples t-test, here's a list of the assumption testing, or the assumptions that need to be met. First of all, there's normality, and normality assumes that the population distributions are normal, and that's each population distribution. So normality should be examined for both groups individually. The t-test is really robust in the face of moderate violations for this assumption, especially when the researcher is using a two-tailed test, or the samples are rather large or not that small, usually more than 30, most people say, or most statistics books say. To check for normality before doing a t-test, researchers have a few different options. One is to create a histogram and examine normality. Also, statistics such as Shapiro-Wilks or Kolmogorov-Smirnov tests can be used. On the histogram, really what you're looking for is a symmetrical bell-shaped curve, and you can see an example of a nice normal distribution here. When you're conducting the normality test, non-significant results actually result significance levels above a 0.05 indicate tenability of the assumption, or that normality can be assumed. So you want to look at normality. The second assumption that a researcher or you want to analyze when you're doing a t-test is homogeneity of variance, or equal variance. Equal variance assumes really that the population distributions have the same variance. Remember, we talked about this earlier when we were talking about calculations. If this assumption is violated, the averaging of the two variances is really, really futile. If it's not violated, or if it is violated, especially in a t-test, you can use modified statistical procedures. In SPSS, you'll note that there's actually an alternative t-value. And even in most statistical textbooks, you'll notice that there's actually two different ways to calculate t-values based on whether or not equal variance can be assumed. Homogeneity of variance is usually tested using Levene's test for equality of significance. And again, a significance level of larger than a 0.05 indicates that equal variances can be assumed. So, and then a significance value of less than 0.05 indicates that equal variance cannot be assumed and that the assumption is not tenable. So really what you're looking for here is a Levene significance level of above a 0.05 for this assumption to be tenable. Additionally, what you want to make sure also with an independent samples t-test, and we talked about this earlier, is that the scores of the two samples are completely independent of each other. Remember, they're two separate groups. If the scores are related and you're looking at one group, then you're better off using a paired sample t-test. And finally, in an independent samples t-test, this is more of a practical matter, but you need to make sure that your n for each of your groups is reasonably large enough in order to have adequate statistical power. That is, remember, statistical power is the probability of rejecting the null when it is false. And generally what you're looking for here is a reasonably high power, usually around a 0.7 or ideally a 0.8. So you want a large enough sample size for each of your groups. So these are things that you want to make sure that a researcher wants to make sure of prior to conducting the t-test. So now we've talked about the assumption testing that's going to be done prior to the calculating the t-value, and then also calculating the effect size. Let's talk about what needs to be reported in an APA results section. Now let's take a look at a few of these items a little bit closer and how they should be reported. When reporting an APA or reporting results for an independent samples t-test in an APA results section, you need to state the statistical results, the t-value, the alpha level, and the effect size, as you can see in the first two lines here. After stating the actual statistical results, you need to make sure that you communicate what those results mean. So let's go back to the example that we've been using of our online students participating in an online statistics course using either video conferencing or discussion board. Here you'll see that the researcher found a statistically significant difference because the alpha level is less than 0.05. And by inspecting the means, the researcher was able to determine which group scored higher. So he or she may communicate the following. Students who used video conferencing for online communication had statistically significant higher course points than those who used discussion board for online communication. And this can be seen with the with the means here. The one group had a higher mean than the other. Since the Cohen's d is 0.1, that means it's a small effect size, so the effect size was small. And then let's say the power was 0.9. Here the researcher would communicate a power of 90%, or 0.9 indicates that if the study was conducted 10 times, it's likely to produce the same results 9 times. That means that the researcher can say that with 90% certainty the results were correct, that the researcher correctly rejected the null hypothesis. And that brings me to the last point here in an APA results section. The decision about the null hypothesis should be stated. So the t-test provided evidence that to reject the null hypothesis. Now, as we wrap up our discussion, we're going to end with putting together an SPSS file for an independent t-test. We end this discussion about the independent samples t-test talking about SPSS because even though it's important to understand the logic behind and the formulas for the independent samples t-test, the reality is that most researchers in the social science fields use SPSS to calculate their statistics for them. So it's important that you set up the file correctly. Here we see an example of what a file set up for an independent samples t-test will look like in SPSS. Here you can see that the grouping variable or the independent variable is on the left. The 1 indicates individuals who were in group 1 or the video conferencing or treatment group, and the 2 indicates that that those are the scores for the individuals in group 2 or the discussion group or the control group. The individual scores on the dependent test variable are entered into the next column. Here we see it under course points. Here we can see that the data from a portion of our sample, 4 from the treatment and 4 from the control group. In the variable view dialog box, you can label the results. So 1 can be treatment, 2 can be control, or 1 can be video conferencing, 2 can be discussion board. So that's whenever you bring up the variable dialog view in SPSS. And when we get into SPSS, you can look more at that. Then what's nice about that, if you label your variables, SPSS will automatically use these labels in your output, which can really be helpful as you clarify your results. Text on SPSS, manuals on SPSS actually provide more information and walk you through step-by-step examples. There's also some tutorials here that will walk you through SPSS. So this concludes our tutorial on the independent samples t-test. Let's take just a moment and review what we talked about. We talked about the definition for an independent samples t-test. We talked about when to use an independent samples t-test, the logic behind the t-test, the formulas for the t-test. We talked a little bit about assumption testing, writing an APA results section, and then finally we ended here with setting up our SPSS file.